In this work, we propose a new representation, namely reconfigurable voxels, tailored to LiDAR-based point clouds. LiDAR is an important method that is widely used in auto-driving systems nowadays. It could provide accurate spatial information, but typically exhibits sparse and irregular spatial distribution, which poses great challenges to detection of small and distant objects. Previous work mainly followed two streams, voxel-based and point-based. Point-based methods like PointNet usually process points individually at the beginning and thus are not able to capture large structures efficiently. In contrast, voxel-based methods quantize the space at first and process information based on the cells. While it allows large-scale structural information to be captured, the trade-off between accuracy and efficiency still remains an open problem. In this work, we follow the voxel-based methods due to their better efficiency in modeling spatial information, but aim at tackling the difficulty caused by the sparsity and irregularity of LiDAR data. Specifically, we propose a generic representation to handle this kind of data. It could achieve adaptive spatial quantization and thus yield more stable local features in sparse regions. With high efficiency and good scalability, it could significantly improve the detection of small and distant objects. Here we show an example of LiDAR data in the bird view. The left part illustrates how we constructed the representation. For the central voxel, it has 4 neighbors in the XY plane. What we do is to devise a mechanism to adaptively reconfigure these 4 neighbors according to the spatial distribution of LiDAR data. The right part shows that our representation could significantly elevate the imbalance of points from different voxels, and thus mitigate the difficulty of extracting features from sparse regions. To sum up, reconfigurable voxels is a more stable representation with strong locality and high efficiency. Here is the overview of our pipeline. A voxel-based framework basically consists of 3 stages: voxel feature extraction, CNN-based backbone, and finally detection head. Our reconfigurable voxels is generic representation that can be utilized in the first stage. As shown in this figure, this is the multi-resolution case of a method. For each voxel is 4 neighbors, could bias random walk to dense regions or another resolution, and then we integrate the central voxel feature and its neighbors feature together and scatter it back to its central voxel location. With this approach, the voxel feature could implicitly depict the local structure information with better stability. For experimental setup, we use KITTI for basic validation and analysis, while use nuScenes and Lyft for validation on large-scale datasets. For metrics, we use their official metrics for fair comparison with baselines. Also validate its efficacy under different metrics. Firstly, we make a complexity analysis to evaluate the difference of our method in terms of efficiency. Because we only introduce constant operations for each voxel in the procedure, the complexity will increase from On to On plus m. As the ratio of n to m increases, the effect will decrease. Experimentally, Table 1 shows that adding our method into 2 frameworks do not influence their real-time performance. Then, here are 2 experiments on KITTI. We can see the improvements are consistent and significant for different frameworks and voxel resolutions, both for small and distant objects. And as we expect, the improvement becomes more obvious as the distance increases. Then we conducted experiments on large-scale datasets. Firstly, on nuScenes for distant objects farther than 20 meters away, methods improved the NDS by about 5%. In terms of small objects, both on nuScenes and Lyft, the detection performance for almost all categories of small objects could be improved at least 2% precision. As for the overall performance, it could also consistently improve the baselines, both for heavier and real-time detectors. Qualitatively, we realized some examples of our representation. The top line shows the dilated voxels with the regional neighbors layout, while the bottom line is ours. From this figure, it can be seen that our representation could cover more meaningful regions according to the local spatial distribution. Therefore, it can be expected that this representation could ease the learning burden of the following backbone and heads in the detectors. In conclusion, we propose a novel representation for handling LiDAR-based point clouds. For future work, alternative representation and its generalization was further exploring. Please check out our paper for more details. Thanks for watching.